Today we shall discuss about the polymer synthesis by ionic chain polymerization. Till now we have seen the addition chain polymer synthesis by initiation with free radicals, and those free radical sources could be different from chemical initiators which can decompose at the polymerization temperature and release free radicals. Those free radicals are highly active. Those active radicals initiate the monomers and carry out the proper polymerization through various steps of initiation, propagation and termination. And you have seen there that the molecular rate is controlled by chain transfer reactions, transfer of their radical activity to various species present in the polymerization medium, and it controls the molecular rate. And sometimes it is necessary that there is deliberate need of deliberate addition of chain transfer agent in order to control the molecular weight, in order to keep the molecular weight at a desired level. Also, the distribution of molecular sizes, those are also controlled by the chain transfer reaction. Apart from this, there are possibilities of chain transfer to solvents, chain transfer to monomers, chain transfer to initiators, chain transfer to your impurities, all those things that can happen. Those should be avoided. For that, it needs a proper selection of monomer, initiator system, a monomer initiator solvent system, control of temperature, and also that way one can prevent the preparation of production of formation of polymer branches there, because the chain transfer can also occur to dead polymer molecules. So, in order to avoid those things, one should be careful, must have a proper control system, so that one can get well defined polymer properties including molecular weight. Okay. And you have seen there that there is chances of auto acceleration. Do you remember what is auto acceleration? I told auto acceleration that can occur, that can happen during polymerization, polymer synthesis as a result of temperature increase, because these polymerizations are highly exothermic polymerizations. So, the reactor system should be such that heat generated during polymerization should be properly dissipated, properly removed through by the with the help of condenser system, or through flowing of some coolant throughout the through the reactor. Otherwise, if the polymerization is carried out in bulk also, in bulk polymerization, since there is no solvent, monomer acts as the solvent, might act as the solvent of the polymer. So, that increases the viscosity of the polymerization mass, and that increase in viscosity becomes a problem, because once the viscosity of the polymerization system increases, there your termination rate of termination decreases, and due to decrease of rate of termination, there might be sudden increase of polymerization rate, propagation rate, and that causes the auto acceleration to effect. And other names of auto accelerations are Tromsdorf effect, or Norris-Smith effect, or gel effect, because it actually leads to gelation, means solidification of the polymerization mass, which leads to actually wastage of the polymer batch that cannot be processed or that cannot be handled, and the reactor system can also be damaged. So, there are so many different problems. In order to avoid all those things, one must be careful, so that no acceleration, auto acceleration kind of thing happens. And before polymerization to occur, you have to be careful about the inhibition by other agents. Inhibition means even if you use adequate quantity of initiator, adequate concentration and quantity of initiator or suitable initiator in the polymerization system, what can happen? This it may not give that efficient initiation of the monomers, and you may not get polymer even. So, then you have to think there might have been happening this inhibition process. What is inhibition? There may be some certain free radicals which are stabilized free radicals. So, if there is a stabilized presence of stabilized free radicals, those stabilized free radicals can scavenge these free radicals generated, during the polymerization. If those free radicals are scavenged or intermediate your growing chain radicals of intermediate size, if those are scavenged, then one cannot get proper growth of the polymer. Okay. So, that inhibition effect should be removed, as well as sometimes the polymerization is controlled by taking some retarding agent. It may not be, the polymerization may not be inhibited, that means inhibition means total stoppage of polymerization, no growth, but one can control the rate of polymerization by using certain retarder molecules. Those retarder molecules retard the polymerization growth, polymerization rate. That means the rate of polymerization may be little lower. Otherwise, it can may be required in some cases where this due to high rate of polymerization, there may be sudden rise of viscosity and may lead to say gel effect, lead to gelation condition. So, in order to avoid that in the initial period of the polymerization, people can use some retarder also. So, that initially the polymerization rate is kept under control. So, these are the things you have seen there. So, I have summarized the things what you have there, what you have seen, and you can compare the polymerization rate initiated by different means, say free radical initiation, photochemical initiation, redox initiation. You compare the rate and the dependence of the parameters on the molecular weight and molecular weight distribution. Okay. And you have seen what is called kinetic chain length, all these things, how this kinetic chain length is related to various rate constants, rate constant for termination, rate constant for propagation, rate constant for initiation. Those things are included in those equations. So, you see how they are related. Kinetic chain length nu is equal to related to those parameters, okay, Kp, Kt, Ki, as well as your what is that called Ri, and the initiator efficiency factor. So, they are related, you have seen, I have shown you those things, and you please go through books. I have mentioned the books, there is fundamental books I have mentioned, Billmer's book, or book by Professor Pigos, or book by Professor Seymour and Karahar, or any other book, you can fundamental polymer science book, you will get all those things there. Now, today let us see how this polymer addition chain polymers can be manufactured or synthesized or prepared by ionic polymerization technique, ionic polymerization principle. You have seen it needs polarization of the olefinic double bond. It needs, you see, this is the olefinic monomer, this is the olefinic monomer. Now, it can have substituents on these carbons, 2 carbons, there are 2 substituents here, 2 substituents here. Now, the presence of substituents actually influence the pi electron cloud over here. That means, either that can help to break this pi electron pi bond homolytically, or that can polarize this thing. Now, this polarization depends on the electron withdrawing and electron donating nature of the substituent present over here. Here you see, this is homolytic cleavage producing free radicals, and on one side one initiator free radical can combine, leaving behind this free radical for addition of further monomer units. So, growth of polymer chain by free radical mechanism. Here you see the pi bond is polarized, positive side and negative side. Due to this polarization will be affected by the presence of the substituents. Look at this molecule here. Now, this is a substituent Y, and if it is electron donating type, you see this substituent will be positively charged center, and due to increase in electron density in this pi bond area, so what will happen, this carbon will assume negative charge, partial negative charge. So, now if there is some this will help initiation of a monomer, and I told you it needs a stability of the system. Now, this stabilization can be can be obtained by delocalization of the charge over here. You can see this resonance stabilization through delocalization can occur, and once this is stabilized, and that stabilization depends on the nature of the substituents present over here. Okay. Here also you see one example, this styrene, how it stabilizes because of this aromatic ring, a delocalized system, electron system, and in this case you see, as opposed to the previous molecule, here you see substituent is electron withdrawing in nature. That means, it is a little more electronegative in nature. So, due to that reason, it actually can draw pi electron cloud from this pi bond. So, this carbon will be positively charged and this carbon will be this your substituent will be negative charged. So, this way we can see if the molecule is like this, say acrylonitrile. Okay. Acrylonitrile, in acrylonitrile the CN group is electron withdrawing nature type, electron withdrawing type group. So, it actually makes this carbon positive and this carbon negative. Okay. And you see, due to delocalization, it can stabilize this chain species. Now, here is a table. These tables are available in books also. Now, different monomers are there, olefinic monomers, ethylene, propylene, isobutylene, dienes, styrene, vinyl chloride, vinylidene chloride, vinyl fluoride, tetrafluoroethylene, vinyl ethers, vinyl esters, acrylic and methacrylic esters, acrylonitrile. Now, the polymerizability of these monomers by various initiation principle, initiation mechanism, it is shown. The positive means it is possible by that mechanism, negative means it does not respond to that initiation. So, positive means it respond to that radical polymerization or cationic polymerization or coordination polymerization. Coordination polymerization I will not be able to cover over here because of the time shortage. I have to cover many things. So, if I get time afterwards at the end of this course, I will cover as well as the copolymerization of various monomers, how various monomers enter into copolymer structure in alternating way, in block way, in random way, depending on the reactivity ratios of the monomers. So, I will discuss later if I get time, otherwise you have to look into book. It is not very difficult to understand, you have to go through the book and you have to learn from there. If you need my help, you come to me, I will explain before you. Now, here you see coordination polymerization. What is coordination polymerization? You do not know. Coordination polymerization means the polymerization of these olefinic monomers having certain substituents which can lead to isotactic, atactic, syndiotactic structure. I mentioned before that. Do you remember polypropylene? Polypropylene, there is a possibility of formation of isotactic, syndiotactic and atactic structure of polypropylene because of the chiral center present on that carbon atom I explained to you earlier. So, that polypropylene it leads to isotactic PP, syndiotactic PP and atactic PP. This is an useless polymer. Now, if certain percentage of this atactic PP is produced in a batch, so this cannot add to mechanical and other properties, mechanical strength, other properties. So, isotactic and syndiotactic PP is desirable, and for that purpose it needs to be specifically prepared or manufactured. So, this polymerization is known as stereospecific polymerization. And stereospecific polymerization is carried out by Ziegler-Natta catalyst, which are organometallic compounds that undergo specifically that produces specifically either isotactic structure or syntactic structure with no atactic structure. One can use other initiators for polymerization, other catalysts for polymerization of this polypropylene or something like that. Not only that, today the various grades of polyethylene I mentioned, LDP, SDP, very low density polyethylene, LLDP, etc. These have been possible only because of this stereospecific polymerization or Ziegler-Natta catalyst that gives highly specific structure. So, that is actually called coordination polymerization, that occurs through coordination mechanism, because say aluminum trialkyl and titanium tetrachloride, aluminum trialkyl, combination of aluminum trialkyl and your titanium tetrachloride, that is a combination of this organometallic catalyst. Huge numbers of catalyst combinations have been, efficient catalyst combination have been developed, and today so many different manufacturers, they are manufacturing these polymers and coming to the competition in the market because of this Ziegler-Natta catalyst. Here you say, it is to be noted that turpentine, styrene, isobutylene and ethyl vinyl ether were polymerized over a century ago by the use of cationic initiators such as tin tetrachloride, boron trifluoride and iodine as initiators or catalysts. While pure Lewis acids such as boron trifluoride or aluminum chloride are not effective as initiators, a trace of proton containing Lewis base such as water is highly effective. The Lewis base coordinates with the electrophilic Lewis acid and the proton acts as actual initiators. Since the cations do not exist alone, they are always accompanied by a counter ion called Gegen ion. So, now we are going to explain this cationic polymerization, how this principles of cationic polymerization. Now, you have seen the kind of monomer, say isobutylene is a monomer which is which contains 2 methyl groups which are electron donating in nature to the pi bond. So, it can, due to the donating electron donating nature of this methyl group in the molecule, isobutylene, due to the electron donating nature of this molecule, it forms a cation, carbocation, and that carbocation is very much effective in adding incoming monomer, adding to incoming monomers, and that causes polymerization. And this kind of polymerization is carried out in highly purified condition at very low temperature. This is an advantage. Now, free radical polymerization, you see, those are exothermic in nature, and if those are free radicals are to be generated there, it needs induction period and time temperature also. At that temperature, the initiator is raised to that temperature for its decomposition. So, benzyl peroxide, it acts efficiently between 70 to 80 degrees Celsius. So, raising the temperature of a reaction mass to that temperature level, what happens beyond that, there will be exothermic polymerization, means huge heat generation. So, that raises the temperature to a very high level, and that becomes difficult to control the temperature in the polymerization reactor. Now, if the polymerization could be initiated at much lower temperature, then you can get well defined properties of the polymers. So, here this cationic polymerization or anionic polymerizations, these are carried out at very low temperature, although they are exothermic polymerization, but since they are carried out at very low temperature. So, thermal control or polymerization control, overall control over the polymerization it becomes very easy and in a very purified system. Let us see. Now, this shows the scheme of polymer synthesis by cationic means. As I mentioned, it is there, it needs a Lewis acid as a catalyst, like say aluminum chloride or boron trifluoride, this is a Lewis acid, and for effective, because this Lewis acids alone cannot initiate, I have mentioned. So, it needs a co-catalyst as a Lewis base, proton containing compound. Now, a trace amount of this proton containing compound, say here it is water along with this boron diphosphide, it forms a complex. This complex is known as catalyst co-catalyst complex, catalyst co-catalyst complex, okay, H plus BF3OH minus. Okay. Now, since the required activation energy is very small, this reaction may occur at very low temperature. Another important point for this kind of polymerization by cationic mechanism, activation energy of this formation of catalyst co-catalyst complex as well as initiation and propagation is very low. So, this polymerization can be carried out at very low temperature, whereas in case of free radical chain polymerization, the activation energy is high for initiation or free radical generation and initiation both and propagation. So, there it needs high temperature for carrying out the polymerization, but here since the activation energy is low, so this can be carried out at very low temperature. Now, look at the initiation step. This is a monomer isobutylene having 2 methyl group on its backbone, and this is the catalyst co-catalyst complex, and this catalyst co-catalyst complex initiates this polymerization by donating this proton to this molecule. Donating this proton to this molecule means here it is H plus. So, it becomes minus. So, H plus adds to the CH2 becoming CH3, and this center becomes positive. This center becomes positive. Now, since this is positive, this is a cation, and the other part of the catalyst that anion, that is known as Gegen ion, that remains very close to this thing, this growing center, cationic center. So, this remains at the vicinity of this cationic center. Now, once this another monomer comes in between, so that this adds to this, that means it polarizes, that already it is polarized because of this presence of this thing, and that can easily initiate that, or easily it can easily add to that monomer. Here you see rate expression, rate of initiation is equal to sum rate constant into concentration of the catalyst co-catalyst complex and the monomer concentration. As before you have seen that the rate expression is very simple, sum rate constant, concentration of the catalyst and concentration of the monomer. You can say, sir, here catalyst is not consumed, why it is then included? Here you see it is added to this thing, there you see catalyst concentration is included in this rate expression. You will see later that this your kinetic chain length or polymerization that remains independent of catalyst concentration, and you will see that one event of initiation by this process can lead to large number of polymer chain growth. Look at the propagation. This carbocation and Gegen ion complex, when it comes close to a new fresh molecule, then that adds to gradually it continues addition to this site, cationic site, and it increases its length, and this is actually known as macrocarbocation. Macrocarbocation, actually here it is not shown with the bracket, it should be shown with the n number of units, then we can say macrocarbocation. You can write that way, macrocarbocation, the length of which may be huge. Now, once this macrocarbocation is formed, then it requires to be terminated. That means, as before in case of radical chain polymerization, you have seen the sequences of events there, initiation, propagation and termination. Here also initiation, propagation and termination steps are there. Look at the rate of propagation here, as before also here as that of your radical chain polymerization, Rp was equal to Kp into monomer concentration and growing chain concentration, growing free radical chain concentration. Here instead of growing free radical chain, you have taken a concentration of macrocarbocation. As in case of free radical chain polymerization, you have seen the estimation of that of the concentration of the growing free radical chain was very difficult because of transiency, because of very fast process. Here also it is not possible to determine or to estimate the concentration of this parameter. So, here also you have to evaluate this carbocation concentration of carbocation. Now, let us look at the termination step. Now, termination here can occur by dissociation of macro carbocation Gaggenheim complex. You have seen in case of free radical chain termination there that occurs by two different processes. What are those processes? Coupling and disproportionation. It is a kind of disproportionation here. It is a kind of disproportionation. So, a polymer molecule is produced with terminal unsaturation, means you see this cation is to be killed. So, if some proton is removed from a carbon atom attached to this carbocation carbon, then there will be negative center. So, that negative and positive center will form a double bond and that end of that polymer chain will be unsaturated. So, a polymer molecule is produced with terminal unsaturation plus the original complex. So, original complex is regenerated here at the termination step by this macro carbocation decomposition or dissociation. So, original complex catalyst co-catalyst complex is regenerated and that is still active as it was active in the beginning. So, the conclusion is many kinetic chains can be produced from each catalyst co-catalyst complex. You read it as many kinetic, not kinetics. It is many kinetic chains can be produced from each catalyst co-catalyst complex. Have you got the beauty of this system? One complex, one isolated complex molecule of catalyst co-catalyst, if it is formed, that will initiate one polymer chain that will grow to its fullest length, then it will be terminated. At the point of termination, that catalyst co-catalyst complex is regenerated. That means, it will again come back to the initiation step. So, only one complex, that means, it says that a very small concentration of catalyst co-catalyst complex can produce large number of polymer chains of very high molecular weight. Do you understand? Now, there can also be termination by other technique, termination by chain transfer to monomer as before in case of, as you have seen in case of free radical chain polymerization. Here you see this is, here it is shown macro carbocation, n number of units are there and at the terminal unit this cationic center is there that adds to this monomer. Monomers become initiated and it becomes dead. So, it transfers it cationic center to a monomer, transfers its cationic center to a monomer and producing a newly initiated monomer which can continue to grow producing large number of polymer molecules. Here you see there are two ways, both the processes can occur simultaneously. One catalyst co-catalyst complex that initiates large number of polymer chains. At the same time, if the termination occurs by transfer reactions to monomer, then that also initiates, it becomes dead and initiates a new chain by starting another. That means, it is a relay process, it is a kind of relay process. It is dead starting another chain to grow, relay process. So, here also you see rate of transfer is equal to KTR m plus. Now, transfer to polymer results branching. Now, transfer to monomer there is no chance of branch. Now, if the transfer to polymer results occurs, then what will happen? Here you see at the terminal point this cationic center is transferred to a monomer, but if it interacts with a dead polymer molecule, if this cationic center is transferred at the midpoint of any polymer chain, at the midpoint or any point of the polymer chain in the backbone polymer backbone chain. So, some cationic center will be produced there like this. So, if some hydrogen, a proton is snatched from here, then it will be this center will be cationic, this center will be cationic, sorry, suppose this one or this one, cationic center. Once this cationic center is produced here, then it will further add on monomer and produce branch. So, through the analysis of polymer structure, one can see what kind of termination reactions occurs in this polymerization or cationic polymerization.
What decides the termination, like what decides the dissociation of the complex? In the previous cases, what decides the termination, like the dissociation of macrocarbocation?
You see, in the system, this active center is present. It is a very good question. Active center is present in the system. Now, surrounding that center, what are the agencies present? Monomer and polymer, isn't it? Monomer and polymer. Now, it is that means for this kind of transfer reaction, some activation energy is required for transfer to monomer or to polymer. If that activation energy is not available to this cationic center, growing cationic center, then it can snatch or it can leave, or what can happen? It can leave this cationic center to other polymer or other monomer, or another growing chain or another species of catalyst co-catalyst complex that is not shown here from the carbon, say now here you see this hydrogen can be taken by some other species present surrounding this terminal cationic terminal macrocarbocation center. So, if this is removed, this way, one proton is removed. So, this will be negative center. So, what will happen? It produces a unsaturation. So, it cannot be specifically said what is the driving force or what are the reason, but you can say you can explain it thermodynamically through activation energy terminology. Okay. Activation energy may not be sufficient for transferring this activity to a monomer or polymer or other things. Rather, any other agency present surrounding or very close to or vicinity of this your end, that can snatch some hydrogen and creating some unsaturation, and this way it gets terminated. That means, this cationic center is actually broken, destroyed or killed that way. That is called self dissociation or self termination. Here also you have to assume this steady state phenomena, as you have seen, in order to find out the growing free radical chain concentration. Here also you have to find out this parameter carbocation concentration of the macrocarbocation. So, by steady state concept where R I become equal to R T. So, you can get this M plus, this is equal to K I C M by K T. Here the concentration terms, this is the rate constant for termination. Okay. Now, you substitute the value of this M plus concentration of carbocation, this term to this rate equation for propagation. There you can find K prime including these 3 rate constants in within K prime. Okay. overall rate constant and concentration of the carbocation, concentration of the catalyst co-catalyst complex and the monomer. So, it is dependent on monomer concentration and this thing Rp. Now, what is dP? Decay polymerization, as you have seen, Rp over Rt. Now, from this Rp over Rt you find here, you see it is independent of this degree of polymerization. Degree of polymerization is independent of catalyst concentration, because you have seen these catalysts are regenerated and that goes for reinitiation of polymer chain, but here it is little different from that of free radical chain polymerization. It can reinitiate only after it assumes adequate length of the polymer chain. In case of free radical chain polymerization, that reinitiation occurs due to transfer reactions, that means premature transfer reactions. Here it does not happen due to premature transfer reactions. You understand? So, premature transfer reactions are not occurring here. That is why these ionic polymerizations are much more effective and gives well defined properties of the polymer. So, provided one can have that facilities of that control systems for carrying out this polymerization, because thermal control, as it is very difficult to control at very high temperature, it is also equally difficult at low temperature, is not it? You have to maintain the low temperature, because these kinds of polymerization is carried out at minus 100 degree Celsius. So, there also you have to maintain that low temperature, and that is also little expensive, but polymerization control can be obtained here. So, if one wants to synthesize polymer, manufacture polymer by cationic or by ionic polymerization, if he has the facilities of that control, that infrastructure for maintaining that very low temperature, he can have better control over polymerization, because you know in any reaction carried out at higher temperature, that is difficult to control, the kinetics becomes complicated. I think you will agree with me. Kinetics of a process, kinetics of a polymer your chemical reaction becomes complicated if it is carried out at high temperature, because the kinetic energy of the reacting species will be difficult to control, and that can lead to random paths leading to random products. Okay. So, for that reason, if the reaction can be carried out at low temperature, provided it is so active, it can be carried out at low temperature and one can get very good control over the polymerization. If the chain transfer is dominant in the termination process, if the termination is dominated by chain transfer to monomer or to polymer, then you see this dP is independent of either monomer concentration or catalyst concentration. So, regardless of termination mechanism, the molecular weight of a polymer produced by cationic process is independent of initiator concentration or catalyst concentration. Polymerization temperature minus 100 degree Celsius, hydrocarbon solvent of low dielectric constant should be used, because that controls the polarizability or the your activity of the ionic centers in the polymerization. If it is highly polar solvent, no cationic polymerization. So, for this cationic polymerization, very stringent requirement should be required, very stringent requirement, and probably you have got this got one point, important point, that is by such cationic process one can get very high molecular weight product and one can get very high productivity, that means polymerization rate also, that means the polymer can be produced at a very fast rate. Okay. So, productivity of synthesizing or manufacturing polymer by ionic polymerization will be higher. At the same time, you will get high molecular weight polymer. At the same time, you will get polymer of well defined properties. I mean, properties are dependent on the molecular weight, molecular size distribution. Okay. It will give you very controlled size distribution. So, for this reason, cationic polymerization is a very good process, provided you have that adequate facilities for carrying out such cationic polymerization. Now, look at this statements written over here. Polyisobutylene is a tacky polymer, means your tackiness and stickiness, these are the two terminologies. Sticky, you know stickiness. What is stickiness? Stickiness means if anything sticks to a surface, it is a surface property, that is called stickiness. That means, if there is some adhesive on a surface, if you adhere a paper, that paper will stick to the surface, that is stickiness. Due to the stickiness property, this paper becomes adhered onto the surface, on a surface, substrate surface, if there is some adhesive action. What is tackiness? Now, if you take two polymer surfaces, if the surfaces of those two polymers are sticky, then those two polymer surfaces can adhere to each other, that is called stickiness. Anyway, tackiness. Tackiness, if it is tacky, then only it will adhere to this another polymer surface. So, polyisobutylene is a tacky polymer with a very low glass transition temperature. Say, of course, the glass transition temperatures of these rubbers or these kind of polymers are lie around say minus 65 to minus 75, minus 80, like that. For this Tg of polyisobutylene is minus 70 degree, and this is because of its tackiness property. This polymer is used as adhesive, caulking compound and a chewing gum base. Similarly, polybutadiene rubber is also used as a chewing gum base and an additive for oil properties, for oil. So, these are the use of this polyisobutylene. Now, there is a very good polymer known as butyl rubber, which is a copolymer of, who can say butyl rubber? Who said butadiene? No. Butyl rubber is a copolymer of isobutyl
rubber and acrylamide.
isobutylene I am drawing this structure. This is isobutylene, this is isoprene. Now, this is actually 1 to 3%, somewhere you can see up to 10% can be used. So, this is a copolymer of this isoprene unit in polyisobutylene. Why that is required? Now, if you take a polymer of this isobutylene, what it indicates? The backbone is saturated. Please note it, this backbone is saturated. This way if you continue to increase the number of units, the backbone is saturated. So, it is a saturated polymer, thermoplastic, and a very good characteristics of this kind of polymer is that because of this symmetric structure configuration, symmetric configuration, this polymer, the gas permeability of this polymer is less, and this low gas permeability property is exploited in automobile tire tubes. Now, in your cycles, any motor vehicles, the tires are used, inside the tire there is a tube. Okay. The tube is filled with air at high pressure. So, if the permeability of the air is very high through that tube wall, what will happen? So, every day probably you have to fill the well with air, which is not economic and convenient also. So, for that some polymer is used whose gas permeability or air permeability is very low, and here is a polymer, this is known as butyl rubber. This butyl rubber, a copolymer of isoprene, your isobutylene and isoprene, that is a butyl rubber. Now, here the purpose of introducing this small quantity of isoprene unit there, to create sites for cross linking or vulcanization. Here this polymer is not vulcanizable by sulfur, but this polymer is vulcanizable by sulfur, because this isoprene unit can react with sulfur. In case of natural rubber, in case of polybutyrene rubber or other dyne rubbers, the sulfur is used as a vulcanizing agent or cross linking agent. It converts that thermoplastic polymer to thermoset polymer. So, this polyisobutylene here is used to manufacture, or this isobutylene is used to manufacture this butyl rubber by this cationic polymerization. So, those things are written over here. Another stable polyacetyl polyoxymethylene, polyacetyl means polyoxymethylene, is produced commercially by the cationic copolymerization of a mixture of trioxane and dioxolane. Now, here you go through some books, you will find there are certain monomers, various monomers, how they are polymerized by this cationic polymerization principle. Okay. Hope you have got this point. Okay. Butyl rubber sheet, and not only that, their saturated backbone of very long length. What happens in a butyl rubber chain, butyl polymer chain? So, after 100 to 150 units of isobutylene, one isoprene unit comes for cross linking purpose. So, entire system is symmetric and saturated. So, this polymer is very stable to high temperature. Now, you are riding, you are getting the comfort of these wheels, tires. Do you know how these tires are manufactured? These tires are manufactured by compression molding using tire curing bladder. Apart from using this butyl rubber for making inner tubes, but this butyl rubber is also used for making bladder, which provides pressure to the mold, between the mold and the tire component, green tire, at high temperature of 170 to 180 degrees Celsius. At that temperature, that bladder remains stable, that bladder made of butyl rubber. So, there are various uses of this butyl rubber which can stand very high temperature. If you take natural rubber, because of the presence of this double bond in the isoprene unit, it is not stable towards that high temperature. It will break and the polymer structure will be destroyed. But because of this saturated backbone chain structure, this polymer is stable to very high temperature. Right. Now, let us come to anionic chain polymerization or anionic polymerization by anionic initiators. You have seen that because of the presence of this CN group, C triple bond nitrogen nitrile group. Now, this helps polarization of this pi bond. What happens? This is a catalyst, NH2 minus. This is a catalyst. This catalyst acts as an anionic catalyst. Say polybutadiene is made by anionic polymerization known as leaving polymerization. This is a terminology, leaving polymerization. Why it is called leaving polymerization? You know, you can understand this reaction schemes here, nothing difficult. If you go through it as before, you have seen this cationic polymerization, rate expressions, all those things, and how to calculate all those things, you can easily get it. But few things I am mentioning here, this anionic polymerization or leaving polymerization. Here actually anionic initiators like sodium butadiene, sodium alkyl or amides, these things actually helps in initiation of monomers which are polymerizable by anionic polymerization by these anionic initiators. Why called leaving polymerization? Now, once the polymerization starts, so long the monomer is present in the system, it will not become dead, it will not terminate, it will remain live. How? In case of radical chain polymerization, even if you do not add any chain transfer agent, the polymer molecules will become dead by transfer to monomer or initiator, all these things by various chain transfer reactions or by termination reaction by coupling process or disproportionation process. So, the radical activity of those free radical growing chains becomes dead or killed spontaneously, of course, after growth of adequate molecular size, but here it will remain live. That is why it is called leaving polymerization. Why? It will not terminate. This concept or this characteristics or this behavior has been exploited in producing block copolymers. What are block copolymers? So, I am just showing, suppose you have taken styrene, you polymerize the styrene to produce a block of adequate or desired length, of known length, block of styrene, polystyrene. Say maybe this block length may be say 10,000 molecular weight. Then this center remains alive, it will not terminate. Then you add butadiene. So long the butadiene monomer is present, it will continue to form a butadiene block. As soon as the butadiene is exhausted, it remains alive, then you add once again styrene. So, what you are getting? A polymer of SBS styrene, butadiene styrene block copolymer. Now, it has a unique property. Now, styrene is rigid, polystyrene is rigid and brittle because of the presence of phenyl ring in the backbone chain attached to the backbone chain at every alternate carbon. This is a rigid polymer, whereas polybutadiene, that backbone chain contains only hydrogen substituents. So, it is flexible. So, what you are getting? We are getting a rigid chain followed by a flexible chain followed by a rigid one. So, what it forms? A hard block, it forms a hard block followed by soft block followed by hard block. What happens? This hard block assemble at certain domains, regions known as hard domains. Embedded hard domains dispersed in soft matrix, it behaves like a composite. So, it leads to a thermoplastic elastomer. Please remind me later when I shall cover this elastomer to explain or to cover elaborately about this thermoplastic elastomer. Now, here our scope is limited to discuss details of this thermoplastic elastomers, but I have told you the concept. By anionic chain polymerization you can manufacture this hard, soft, hard blocks as thermoplastic elastomers, since it is living in nature. And as before, here also you see there these your different your expressions for different rates RP, RTR, and by the steady state concept you get this from the steady state concept, get this concentration, then you get this RP, and therefore dP you can get this is monomer and ammonia concentration, and thus the rate of propagation and the molecular weight are both inversely related to the concentration of ammonia, and the activation energy for chain transfer is larger than the activation energy for propagation. The overall activation energy is approximately 38 kilocalories per mole. The reaction rate increases and molecular weight decreases as the temperature is increased, and then you see there are various other possibilities using various other initiators you can do. So, go through the book and read it, you will understand. Thank you.